Okay, so welcome to the third class of Calc 2. And what I want to do today is talk about some of the transitions from algebra to calculus. And so what I want to do is I want to use this as an opportunity to review some things you should have seen in Calc 1 and to pave the way for some of the things we're going to see in Calc 2. One of the things I've found over the years that causes people tremendous difficulty is algebra. Is frequently people understand how to do the calculus, but that's only one part of solving the problem. After you do the small amount of calculus, then you have to do the algebra to get the right answer. So I'm going to have fairly detailed slides going through the algebra in places in excruciating detail. I'm not going to cover all of that in class. This is one of the reasons why I took the time to make detailed slides. So I strongly encourage you to look at the slides carefully if you have any questions or if you're rusty, and then talk to me, talk to the TAs. For this week, the Math 140 and 150 TAs are doing open office hours, so anyone from either class can go to either one. So there's a lot of material to do today, but again, if I'm going too fast, please tell me to slow down, ask a question. You can put something in the chat because I'm also looking on my laptop as well as my iPad, so I should hopefully see something there. All right, so I want to start with something you've hopefully seen before, Pascal's Triangle, but at least show you some new things about it that you may not have noticed before and try to really emphasize why this is so important in calculus. So one of the main themes in Calc 1 is differentiation. How do things change with time? So we're going to review a couple of functions and we're going to discuss limits. And then if time permits, we're actually going to talk about some applications. Newton's method, one of the most powerful ways to find solutions to problems. And if there's tremendous time, which I doubt there'll be today, but maybe later in the semester, we'll talk about applications of all of this to fractal geometry, which has some really interesting applications in everything from biology to economics. All right, so hopefully you've seen Pascal's triangle before, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. There's lots of ways to interpret the numbers here. We'll see later that they come from the coefficients of expanding x plus y to the n. They also are the number of ways of choosing k objects from n when order doesn't matter. And the rule is you basically have two diagonal lines of ones, and then every number is the sum of the number immediately above and to the left, plus the number immediately above and to the right. So if you look at 10, 10 is 4 plus 6, 15 is 10 plus 5. So similar to last time, one of the main tools is FOIL, first outside, inside, last. If we want to multiply two expressions such as a plus b times c plus d, we get a times c plus a times d plus b times c plus b times d. And you can do this for lots of different problems, and you can derive some identities. I'm not going to, again, go through these in great detail, but that's why the slides are here. If we start looking at something like x plus y cubed, well, one way you would do it is you can write it as x plus y times x plus y squared. And we now know how to do x plus y squared. And so when you have a complicated problem, break it into simpler ones. And we'll see this, time and time again, do it again and again and again, make it simpler, make it simpler, make it simpler. And when we expand it out, we get x cubed plus 3x squared y plus 3xy squared plus y cubed. Well, let's put those coefficients in red and bold, 1, 3, 3, 1. And we notice that that's one of the rows of Pascal's triangle. And if we look at what we had earlier, x plus y squared, which we needed when we were calculating x plus y cubed, we have 1, 2, 1. If we wanted to calculate x plus y to the fourth, we could write that as x plus y times x plus y cubed. We know what x plus y cubed is, and now we just multiply that by x plus y. And so this is the start of Pascal's triangle. So I'm claiming that this is what you get when you expand x plus, Preston? Okay. So I'm claiming that this is what you get when you expand out x plus y to the n. What should it be when we have x plus y to the 0? Well, in mathematics, we typically say anything to the 0th power is 1. And so x plus y to the 0 should just be a 1. And this is going to give us a triangle, and the nth row, the coefficients of that are going to be what you get when you expand x plus y to the n. And this is going to be extremely important in proving results in calculus. And that's, of course, the main reason we're covering this today. So we can keep going and we can keep generating more and more rows, especially if we notice each element is the sum of the number above to the left and above to the right. And so, this is just, highlighting, getting from the third row to the fourth row. Well, actually, technically, I guess from the fourth. Well, it's the third row because we're starting with the 0th row. So this is one of the things that's annoying for those of you who do programming in CS. Some languages have you start with the 0th element. Some languages have you start with the first element in a list. You just have to watch and be careful where you are. It's technically convenient to say we start at the 0th row. When my son was young, he realized if I told him, you can only do this 3 more times, he realized very quickly if he starts counting at 0, daddy's a mathematician and he can do it 4 times. So our third row is the 1, 3, 3, 1. The fourth row is 1, 4, 6, 4. And you can see the 1 plus 3 gives 4, the 3 plus 3 gives 6. So how do we prove this? So I'm going to just give you a sketch of the proof and I'll let you look at it in detail later. But if we want to calculate x plus y to the 6th, let's assume we've already done x plus y to the 5th. So technically this is called proofs by induction. And we'll discuss this in greater detail maybe later in the semester. We know what x plus y to the 5th is. And so we first use the distributive property to say x plus y times x plus y to the 5th is x times x plus y to the 5th plus y times x plus y to the 5th. And then we expand out x plus y to the 5th, multiply by x, multiply by y, and then group together terms. And if you think about it, this is beginning to see why we're adding above to the left and above to the right. So there are many properties that we can prove for Pascal's triangle. I wanted to show you one that you may not have seen that does have some really interesting applications in biology and economics. It leads to fractal geometry. So what I'm going to do is I'm going to put a dot if we have an odd number in Pascal's triangle. I'm going to delete if it's an even number. So if we just have the 0th row, it's just a dot because it's 1. If I go down to the 3rd row, it's going to be the following. I only lose the number 2 in the row 1, 2, 1. Everything else is odd. And we can keep going. If I go down to the 8th row, and you can keep going and going and going. And so I wrote a computer program. I've since modified it. So rather than printing it horizontally, it prints things vertically. You get these very interesting fractal shapes. And what I'm doing is as I add more and more rows, I'm constantly squishing the triangle so it takes up the same amount of time. So this is just rotated 90 degrees. So rather than having the vertex on the top, the vertex is on the origin. It was just easier to plot it that way. If you really care, I do have a better link that I've now made that does it. And so there's a short little video I made explaining what this is. So if you're interested, this is a short thing to watch about some of the fractal properties of Pascal's triangle. All right, so now let's pivot to algebra and limits. And this is what we need to get to calculus. So we want to evaluate functions. So what is a function? A function takes an input and gives a unique output. If it can give multiple things, it's not a function, it's a relation. For a function, if I give you an input, if I tell you my location, you can't say the temperature is 32 degrees Fahrenheit and 37 degrees Fahrenheit where you are. No, the temperature is one value where I am. So we often use the letter F for function. Again, whenever possible, try to have notation that makes sense. This is why in calculus, we use the prime often to denote derivatives. So F prime, you can see it's related to the function F. So a linear function is of the form ax plus b, where a and b are fixed constants. So for example, f of x is 3x minus 5, or 7x plus 2, or 4x plus 17. Different choices of a and b give you different lines. So here a is going to be the slope, b is going to be the intercept. And so for 3x minus 5, if we increase x by 1, then y is going to increase by 3. For the second one, if we increase x by 1, y is going to increase by 7. And so if we want to evaluate functions, the simplest thing to do is to just plug in values of x. So we can plot something by putting in a couple of values. And then the more values you put in general, the better sense you have of the curve. Now for a line, we really only need 2 points. 2 points uniquely determine a line. With those 2 points, I can draw it perfectly. But as your shape becomes more complicated, as your function becomes more involved, we need more points to get a better sense of what's going on. So the next one after lines would be quadratic functions. So f of x is ax squared plus bx plus c for constants a, b, and c. You've probably seen this with the quadratic formula to find its roots. Interestingly, you can actually use parabolas to do some interesting cryptography. If anybody's interested, just shoot me an email. It's a little bit more work to find out what the value of the function is now, but again, we can plug things in. It turns out there's a faster way to find the values of a parabola than just plugging in the values of x. And for small degree polynomials like quadratics, it's not that important. But in a lot of applications, when you have polynomials of high degree, and there are times when we have polynomials of degree 10 to the 200, any savings you get is tremendous. And so if anybody's interested in stuff like this, which has wonderful applications in cryptography and modern e-commerce, just let me know. All right, so polynomials. So more generally, we can look at a polynomial of degree n. And so we use the following notation. We use a's with subscripts to denote the coefficients. And to try to make things nice, well, if the leading term is degree n, so we'd have an x to the n, let's call its coefficient a sub n. So the subscript goes with the power. We go all the way down to the constant term, which is a0. And so below, I have a plot of a linear, a quadratic, and a cubic. And what you can see is they all equal the same value at 1, which makes sense because they're all 1 to a power. Beyond 1 to the right, the quadratic is growing faster than the linear, but slower than the cubic. And to the left, it flips. The linear is growing faster than the quadratic, which is growing faster than the cubic, which makes sense because if you have a number that's less than 1, if you cube it, say 1/2 becomes 1/8, which is much smaller than 1/4, which is smaller than 1/2. So the relationship, the ordering changes depending on whether or not you're less than 1 or greater than 1. So the big concept in Calc 1 is that of a limit. So we want to know what happens as we approach a certain value. And so the rule is if I write the limit as x approaches 2, that means x gets closer and closer to 2, but x is never actually equal to 2. It just gets as close to 2 as you want. And so if I give you f of x is 3x plus 5, well, what we would just say is everything is well behaved. As x goes to 2, just replace x with 2. And this is going to then just become 3 times 2 plus 5, or 11. Okay? And if I gave you another way of writing this, is we can write x approaches 2. We can write x as 2 plus h, where h is a small little change. It could be positive, it could be negative, but h is going to 0. What's nice about this is now, rather than saying I'm going to calculate the limit as x goes to 2, x goes to 5, or x goes to negative 17, I'm always doing the limit as h goes to 0. And so in some sense, I'm kind of standardizing the problem I'm doing. I'm always looking at h goes to 0. And so the limit as x goes to 2 of f of x would be the same as the limit as h goes to 0 of f of 2 plus h. And when we plug in, we will of course get the same answer as before. Okay, so more on limits. It's important to remember when h goes to 0, h is never 0. Why do you think it's important that we don't have h to be 0? Well, in the definition of the derivative, which you've seen before, we are dividing by h, and we can't divide by 0. We talked about that in the last class. So it's essential that when we calculate limits, we're never dividing by 0. So if we want to calculate the limit as x goes to 2, for instance, of x squared minus 4 over x minus 2, well, the first thing we could do is we could write it as the limit as h goes to 0, and we replace x with 2 plus h. So we would have 2 plus h squared over minus 4 over 2 plus h minus 2. All right, we expand everything out, do a little bit more simplification. We see the 4's cancel upstairs, the 2's cancel below. We have 4h plus h squared over h. Well, and h cancels, and that's just 4 plus h. And so the limit is 2. And what's nice is this limit makes sense. If you looked at what was going on initially, if you just plugged in x equals 2, we would have 2 squared minus 4, which is 0 upstairs. And we would have 2 minus 2, which is 0 downstairs. We have 0 over 0. So we can't compute 0 over 0. We have to be very careful when we have 0 over 0. This is one of the uncomputables. We can't compute infinity over infinity. We can't compute 0 times infinity. We can't compute 0 over 0. We can compute 0 divided by infinity. That's okay. 0 divided by infinity is just going to be 0. But here we can't do 0 over 0. But if we look at the limit actually makes sense. Now, one of the things in mathematics is the more you know, the more approaches you might find to a problem. And the more comfortable you are with algebra, the more you might see there's other ways of doing things. You might notice that the factorization of the numerator is x minus 2 times x plus 2. Oh, well, I've got an x minus 2 downstairs. The x minus 2's cancel, and then the limit is just going to be 4. So for this particular problem, if you happen to notice that, it would make things a little bit easier. Now, not all limits are going to be easy to just look at and see. And so in an earlier lecture, I think this was actually yesterday's lecture, and for me, yesterday is always the previous class, tomorrow is always the next class. We had these formulas which converge to pi. And if you look at this, and if you were able to see that this is converging to pi, hats off to you. I have no intuition at all looking at this that this should be pi. And if you do have such great insights, what would happen if you replaced all the 2's with 3's? What would that converge to anything nice? Or you replace the 2's with 3 halves, would that converge to anything nice? What would you get as you do those modifications? All right, so now that we have some algebra background, let's apply this and let's get some calculus. So the first concept we want to talk about is average speed. And we saw in the last lecture the power of having units. We did Pythagoras by doing a unit analysis proof. We did the period of a pendulum is the square root of L over G, times some function of the angle by looking at units. And so if we have y equals f of x, maybe make x time and f of x distance from home. And so this tells me how far I am at every moment in time. So without loss of generality, let's just normalize things so that at time 0, we start at home, so f of 0 equals 0. And let's end the trip 2 hours later. And let's say at time 2, we have f of 2 equals 110. So we traveled 110 miles in 2 hours. So here's a couple of questions. What is I?
Shift gears
yes?
Now, and the Port of Lamu has been licensed for a dry run transship.
I'm sorry? So, okay, so we start at 0, we end 110 miles away from home 2 hours later. So which of these problems can we answer? Can we find our average speed, our fastest speed, our slowest speed, our most common speed? Which ones of these can we answer? Anyone want to jump in?
I think you could find the average speed where you would
Yes.
take 110 and just divide it by 2 to find
Perfect.
you travel 55 miles an hour.
On average, we've traveled
On
average
average.
5 miles per hour.
Yes.
But none of the other questions are answerable. For our fastest speed, I could always accelerate a little bit and then slow down a little bit later. I could be traveling at 55 miles per hour the whole time. I could travel 0 for the first hour and then be a speed demon of 110 miles per hour for the second. So the only thing we can answer at this point is the average speed. That's all we can deduce. Okay, so to compute the average speed, we look at how far we've traveled and how much time we've gone. The way cars do this is they look at how many revolutions the tires make, because they know how far the car has gone based on how many revolutions the tires have made, and they look at how much time has elapsed. And the idea is if you want to try to calculate your instantaneous speed, if you look at average speeds over smaller and smaller windows, that should be better and better approximations to the instantaneous speed. So here, the average speed from A to B is just f of b minus f of a, the distance traveled, divided by b minus a, the time elapsed. And so if I give you a linear function, say 3x plus 5, we can calculate the change in distance. And when you plug in everything, you get 3b minus 3a. The change in time is b minus a. Oh, this is nice. So to calculate the average speed, we get 3. So in fact, for linear motion, what's fascinating is that the average speed is also equal to the instantaneous speed. I could try to find the average speed for a quadratic function. So let's say I give you x squared plus 3x plus 1. I'm not going to go through and do the algebra here. You can look at it later. You can calculate what the average speed is from A to B. And it turns out it's not that bad to do. So this is just going through and calculating what it is. Now we could ask, what happens in the limit as b goes to a? So as b goes to a, what would the above converge to?
Is it like an instantaneous speed?
So it will converge to the instantaneous speed, and we know the average speed from a to b is b plus a plus 3. So as b goes to a, what does b plus a plus 3 go to as b goes to a?
Is it 0?
It's not 0. So we have b plus a plus 3 as b goes to a. Does the 3 change as b gets closer and closer to a?
No.
No. Does the a change as b gets closer and closer to a?
No.
No.
So what does b plus a plus 3 go to as b approaches a?
Would it be 2a plus 3?
It would just be 2a plus 3. And if you look at the function x squared plus 3x plus 1, if you take the derivative here, we know that it's 2x plus 3. When x equals a, it's 2a plus 3. So we're beginning to see where this derivative comes from. And so we get that the instantaneous speed, as we said, is just 2a plus 3. Now we can calculate the average speed by looking at small and smaller intervals. So I can start off, let's say I want to figure out what's going on at the point 1. I can take smaller and smaller steps. So what I'm going to do is I'm going to take values of b, f of b, and I'm going to take x equals 1. And so if we go, if b equals 2, f of b is 11, the change in distance is 6, the change in time is 1, so the average speed is 6. And we can see that the average speed is getting closer and closer and closer to 5 as b gets closer and closer and closer to 1, which is our a, which is our starting point. And of course, if we take b equals a, then things blow up. Because if the starting and the ending times are the same, there is no change in distance. There is no change in time. We just have 0 over 0. So it looks like it's converging to 5. This is not a proof, but it looks like it's converging. So now we introduce the definition of the derivative. So the instantaneous speed of f of x at x equals a is the limit as b goes to a of f of b minus f of a over b minus a. Or if we want to use the h notation, it's the limit as h goes to 0 of f of a plus h minus f of a over h. Sometimes rather than talking about the derivative at a, we just talk about the derivative at a general point x. And we denote this by f prime of x. And again, as mentioned, this is really good notation because the prime reminds us that this is coming from the function f that we started with. It's related to that. And so we can now use this definition of derivative to calculate the instantaneous speed for a variety of functions. And the rule in everything in life is start simple, build your intuition, get some examples under your belt, and then move on. So the first one is to start off with 3x plus 5. And so I'm not going to go through all the algebra, but if you look at it slowly, if you go through everything, the limit is going to just become 3h over h. The h is canceled. You just get the limit of 3. And again, if you have any questions on this, please talk to me, talk to the TAs. Linear functions, the algebra works out very nicely when you calculate the change in distance over the change in time. Now, we did this for the function 3x plus 5. When we calculate the derivative, it's 3. The 3 is coming from the coefficient in front of the x. The 5 doesn't seem to matter. So this might lead you to conjecture that if I give you a linear function, f of x equals ax plus b, if you did similar algebra, you would get the derivative as just a. Okay, instead of using a, I guess I used c plus d, cx plus d here. So when we take the derivative, we would get f prime of x equals c. Well, building on our success with linear functions, we could try quadratic functions next. And again, it's worth remarking that there's 2 ways I could have done this lecture. So first I'm doing linear functions and I'm doing quadratic functions. Anybody want to guess what we would do after quadratic functions?
Cubic.
Cubic. So that's one way to do the lecture. Another way to do the lecture is to look at just pure functions, x, x squared, x cubed, calculate the derivatives of those, and then prove some results about derivatives. The derivative of a sum is the sum of the derivatives. The derivative of a constant times a function is the constant times the derivative. If you have that, then you can reduce the derivative of any polynomial to simple combinations of the derivatives of 1, x, x squared, x cubed, and so on. So we could either work with a more general polynomial to begin with, or we could actually restrict ourselves to a nicer subset. And so if I take the quadratic function, 3x squared plus 5x plus 2, let's look at the numerator. So what would f of x plus h be? We put in x plus h for the values of input, and then we expand it out, and this is where we use Pascal's triangle. There's a reason why we started with Pascal's triangle. We need Pascal's triangle to calculate x plus h squared, x plus h cubed, and so on and so on. And if there's time on Friday, I'll talk about what happens if I ask you to take the derivative of a function, maybe x to the 3/2. How would we do something like that? And so we look at f of x plus h, we look at f of x, we subtract, and we see it's 6hx plus 3h squared plus 5h. We now look at f prime of x, we're going to take that divide by h. So we cancel 1 power of h everywhere. We just get the limit as h goes to 0 of 6x plus 3h plus 5. Okay, well, as h goes to 0, 6x goes to 6x, 3h goes to 0, and 5 just goes to 5. So we have the derivative. And now what we want to do is we want to try to get some patterns. We have 6x plus 5, we had 3x squared plus 5x. So it seems clear that the 5 goes to the 5. And with a little bit of insight, we might eventually realize the 6 is equal to 3 times 2 times the power of x squared. And then we have x to 1 power less. And you can do lots and lots of examples and start building this up as a conjecture. Okay. And so anybody want to guess what the derivative would be for f of x is ax cubed plus bx squared plus cx plus d? So what would the derivative of the cubic be?
Would it be 2ax plus b? Oh, I did the wrong one. I'm sorry.
Yep, no problem. We're doing the cubic at the bottom, ax cubed plus bx squared plus cx plus d. Do you want to try that?
Yeah, so would it be 3ax squared plus 2bx plus c?
Perfect. And again, the calculation would be very painful if we had to do this. And this is why we want to develop techniques that allow us to handle x to the n for all n, that allow us to handle any polynomial. We don't want to constantly have to go back to the definition of the derivative every time we have to compute something. And this is why we prove all these results in calculus. This is why we prove the sum rule, the constant rule, all these things, so that we can take a complicated expression and reduce it to a bunch of simpler ones. Okay, and so if we want to calculate ax to the n, we're going to find the answer is na x to the n minus 1. And the key ingredient is Pascal's triangle in terms of expanding things out. All right. So why do we care about all of this? Well, the reason we care is that in general, we're not going to be fortunate enough to have a simple function to work with. But locally, every function is nice. Every good function is locally a straight line. If you go over small enough periods of time, you really can't see the difference in how your speed is changing. It looks like you're traveling at constant speed. Now, how large of a window is that? It might be a second, it might be a tenth of a second, it might be 1/1,000,000th of a second, depending on what your object is. But over a small enough time scale, most objects will look like they're traveling at constant speed. And the point is then we can approximate a generic curve locally with a straight line. And this is the tangent line concept from calculus. And so here we take a quadratic 3x squared plus 5x plus 2, and that's drawn in blue. And then the gold is the tangent line at the point 2. And what you can see is that, a little bit to the left and right of 2, it's really hard to distinguish between them. So I'm going to try to just zoom in. And, it's really hard to see the difference as we move over a little bit to 2. And this is the power of the tangent line. And so how do you calculate the tangent line? Well, we're going at the point 2. And so if x equals 2, the value of y is f of 2, which here is 24. The slope of the tangent line is the instantaneous speed. That's f prime of 2. Well, we know f prime of x is 6x plus 5, so f prime of 2 is going to be 17. So we have a point that's on the line. The point is 2f of 2. We have a slope, which is f prime of 2. And now we can use the point slope form. So the point slope form is y minus f of 2 equals mx minus 2. Or just putting everything together and simplifying, you get y equals 17x minus 10. Although I think it's actually a little bit better to write it as y equals 17x minus 2 plus 24. Because then you can see if I move a little bit away from 2, exactly how much we're changing by. Okay, so what I want to do now is talk about an application. So this is the topic that moved me from leaning more to being a physics major in college to being a math major. I did finish the physics degree, but when I saw Newton's method and just how powerful it was, this is what really pushed me to mathematics. One of the biggest problems we have in math is trying to solve equations, trying to find where something happens. So if I give you polynomials, if I give you ax plus b equals 0, this is not that hard to solve. I just subtract b, divide by a, not a big deal. For the quadratic, you hopefully remember the quadratic formula. The best way to prove this is completing the square, but we get the roots. So we can solve quadratics. There are formulas for cubics and quartics. You can explicitly write down a formula in terms of the coefficients and various roots. Unfortunately, there is no closed form expression for degree 5 and higher. For degree 5 and higher, we have to estimate. The other thing, of course, is just because I write something down or give it a name, doesn't mean I know how to compute it or estimate it. If I tell you the area of a circle is pi, okay, I've given it a name, but unless I tell you how to actually compute pi, it has limited utility. So if we can't find a solution, can we at least find a way to approximate a solution? And if so, how good of an approximation will it be? And how long will it take to get a good enough approximation? So just for completeness, here is the 3 roots of a cubic. You can begin to see why we don't have you memorize these in high school. You could make things a little bit easier without loss of generality. What could we assume about the value a? If we're willing to change the values of b, c, and d, what could we assume is true about a?
That it's a constant.
Right, but which constant value? You can assume a takes on a specific value. What value can you say without loss of generality? We might as well assume a equals
1.
1. Because if a is 0, it wouldn't be a cubic. And I can just divide through by a and get a new value of b, c, and d. So without loss of generality, we can assume a equals 1. It turns out you can also translate. You can replace x with x minus r. And if you choose r appropriately, you can actually make b equals 0 as well. So if you do tricks like this, you can make the formula a little bit nicer, but it's still going to be bad. For the quartic, I apologize, I had to reduce the size a little bit. I think I can blow it up a little bit. So here's the formula for just one of the roots of a quartic. And so even if there was a formula for the quintic, it's unclear how useful this would be in practice to actually do anything with. It's not nearly as nice as the quadratic formula. All right, so I'm going to introduce 2 different ways to find roots of equations. So the first is divide and conquer. So imagine you have a continuous function and it's negative near 0 and it's positive near 1. Can somebody tell me what must happen between 0 and 1?
It has to pass through the x-axis.
It has to pass through the x-axis. You cannot discontinuously move from negative to positive without going through 0. You have to go through all the points in between. Does anybody remember what theorem this is from calculus? So this is the intermediate value theorem from calculus. That if you have a continuous function and you take on, say, the value -1 at 0, and you take on the value of 5 at 1, you have to hit all values between -1 and 5. This past winter, I taught 2 winter studies. One of them was the science of Star Trek with a colleague of mine in physics. If you've ever watched Star Trek, one of the most famous items in the series is the transporter, which allows people to essentially instantaneously move from being on the ship to being on the planet. So that would be an example of discontinuous motion. So we're not allowed to do a jump like that. We have to go through all intermediate points. As an interesting aside, the reason they invented the transporter in Star Trek is the show was being produced with incredibly expensive special effects for the time, and they didn't have the money to build a shuttlecraft in a hangar bay for the first episode, and they needed to get the crew down to the planet. So somebody said, hey, what if we just push a button and now all of a sudden they're on the planet and then we don't have to build the set? Sold. All right. So let me describe the first method. It's called divide and conquer. So if you have a continuous function that's negative at A and positive at B, it has to have a root between A and B. So to find the root, look at the middle point. If the middle point is less than 0, then we know there has to be a root between the midpoint and B. If it's greater than 0, we know there has to be a midpoint between A and that point. So for example, you can use this to guess anyone's birthday in 10 guesses or less. So can I have a volunteer from class? Somebody, I need you to think of a day of the year between January 1st and December 31st. I need a volunteer quickly.
March.
Thank you. Don't tell it out loud. Don't tell it out loud. Okay, you've got a date?
Yeah.
Okay. Is it July 1st?
No,
Is it earlier or later?
earlier.
So with that one guess, I've eliminated half the year. That's much better than going, is it January 1st? Is it January 2nd? Is it January 3rd? Is it January 4th? With one guess, I eliminated half of the year. Okay. Is it April 1st?
No,
Earlier or later?
earlier.
So I've eliminated half again. So now I want halfway between January 1st and April 1st. I'll go with maybe February, maybe 9th.
No,
Earlier or later?
later.
And so you can see every time I guess, I have the uncertainty. And so, I call this shampoo mathematics: lather, rinse, repeat. Keep doing, keep iterating, keep iterating. And so, if I take the function, for instance, x squared minus 3, the roots of x squared minus 3 are plus root 3 and minus root 3. Well, what is the square root of 3? Well, we can now approximate this. If we look at x squared minus 3, if we take 1, we get -2. If we take 2, we get 4. So we know there's a root between 1 and 2. We look at 1.5 and we see f of 1.5 is negative, so there's a root between 1.5 and 2. We take 1.75 and we see that the function is positive there, so the root is somewhere between 1.5 and 1.75. So if we do 10 iterations, we get that the root is somewhere between 1.7304 and 1.7324. And the correct answer is 1.73205, approximately. So the problem with divide and conquer is it's expensive. Every 10 iterations, we reduce by a factor of 1/2 to the 10. Well, what's 2 to the 10? 2 to the 10 is 1024. 1024 is approximately 1,000. So essentially, every 10 times you do this, you gain 3 decimals of accuracy. So we've basically got about 3 decimals of accuracy after doing this 10 times. If we wanted another 3 decimal digits, we would have to do this another 10 times. So this method works, but it's slow. So enter calculus. It shouldn't be surprising that we get a better answer when we use calculus, because the advantage of using calculus is we know more about the function. With Newton's method, we use not just the value of the function, but how rapidly it's changing to try to approximate things. And so what we do is, given some guess, xn, we look at the tangent line to the curve at that point, draw the tangent line, see where it hits, and call that our next guess, and then we keep iterating. And when you finish doing all the algebra, you get a formula for the n plus first guess, xn plus 1, is your nth guess, xn, minus f of xn over f prime of xn. So let's draw a picture. So here's my function y equals f of x. I've got my point x naught, my initial guess. I draw the tangent line, and then I say, I'm going to approximate my function by the straight line here. And I'm going to see where that hits the x-axis, and I'm going to label that point x1 my next guess. And we check and see, is this the root? And it's not, so we do the method again. And so, do I show it again? No, I guess I don't show it again. All right, sorry. Thought I had drawn the picture again. So we just keep iterating again and again and again. So let's try it with f of x equals x cubed, I'm sorry, x squared minus 3. The roots are going to be root 3 and minus root 3. So if we take as our initial guess 2, we plug in for f of 2, we get it's 1. This is not 0. So we haven't found the root. What's f prime of x? F prime of x is just 2x. So when x equals 2, f prime of 2 is just going to be 4. So now we draw the tangent line over here, and we see where that hits. And so we have the point 2f of 2, which is just the point 2, 1. The slope is f prime of 2, which is 4. So we can write down the tangent line. And again, this is one of the big themes of Calc 1, is the tangent line is a great approximation for the function. So we get y minus 1 is 4 times x minus 2, or y equals 4x minus 7. So we want to see, where does this hit the x-axis? So when this hits the x-axis, what's the value of y going to be?
0.
0. So we plug in y equals 0, we get 4x minus 7, so x is 7/4, so 1.75. And so already our first correction is 1.75, which is pretty close to 1.732. And what's nice is this will always give us a rational approximation. So we can try this again. We can use 7/4 and find the new tangent line. And again, when we do the algebra, and see what it is, let's see, I'm just going to skip ahead. We get our next guess is 97/56 after you do the calculation. Ah, good. Here I redrew the line. So here's the red line, which is the next iteration. And you can see it's looking pretty close to the square root of 3. So we get 97/56, 1.73214 versus 1.732050. That's not bad for just 2 guesses. We can go a little bit further. We can actually write down a general form. And when you do the algebra, you get xn plus 1 is 1/2 xn plus 3 over xn. Whenever you see a formula, you want to ask, is this reasonable? The best possibility for you is if you took xn to be the square root of 3, if you were actually perfect with your guess. Well, if xn was root 3, we'd get root 3 plus 3 over root 3. That's just root 3 plus root 3, which is 2 root 3, divided by 2, that's just root 3. Wonderful. So if we happen to be at square root of 3, we stay at the square root of 3. If we have a really bad guess like xn equals 10, we would have 10 plus 3/10, take half of that, that's about 5. You can see it's crashing down to the root. So it turns out this converges very rapidly. I'm not going to prove it, but every time you iterate, you double the number of decimal digits of accuracy you get. So if you look at the second guess, we said it was 97/56. The third guess is 18,817 over 10,864, 1.73205,081. And the correct answer is 1.732050807. So after just 3 iterations, we're extremely close. What I've shown below is where we are after 5 iterations. And I've highlighted in black just how far you have to go before you finally see a difference between the square root of 3 and our 5th approximation. It is absolutely stunning how much better this is than divide and conquer. With just 5 iterations, just the number of decimal digits we have is beyond what your calculators and phones can display. So absolutely amazing. And this is the power of calculus. This is the power of replacing a complicated function with a simpler one. So what I want to do is I want to play a little game. So let's consider the function x squared minus 1. We can factor it as x minus 1 times x plus 1. And we have 2 roots, 1 and -1. So what we can do is we can play Newton's method. We can start off with a guess, and we can see, does the guess converge to the blue root 1? Does it converge to the red root -1? Or does it not converge at all? So if we take Newton's method and we take 1 or -1, we're going to get back 1, -1. Does anybody want to tell me some region of numbers and where they converge to? So can anybody tell me a region that they think will converge to the blue root? If I give you the number -100, what do people think -100 will converge to? Or do you think it's not going to converge? Someone needs to be brave. Where do you think -1 is going to converge? And if so, to where? Or do you think it's not going to converge?
I guess I'm just confused. Like, when you say converge, do you mean like,
So if I keep applying Newton's method and I start with my initial guess as -100, and I keep seeing what numbers Newton's method generates, and I look at the sequence of numbers, do I think that's going to converge to -1? Do I think it's going to converge to 1? Or do I think it's just not going to converge? So we saw before we were converging to the square root of 3 when we started with our guess of 2. What do you think we might converge to here if we start off with -100? Which root do you think we might converge to?
-1?
-1. And what do you think we would converge to if we start off with 100?
1.
Positive. What if we start off with 1/3? What do you think 1/3 might converge to? What would you hope 1/3 converges to?
I'm
1?
just
1. Why would you hope it converges to 1? Because 1 is the... What relationship does 1 have to 1/3 that's different from the relationship of -1 to 1/3? 1/3 has what relationship to 1 versus -1? It is,
a positive number.
it's positive, but related to that, 1 is closer to 1/3. So maybe the hope is that you converge to whichever root is closer. And what about 0? Well, we can't divide by 0. And so if we color it, if you actually do Newton's method, everything that's positive converges to 1, everything that's negative converges to -1. Okay. And now the really interesting slide. Let's look at x cubed minus 1. So if you remember your polynomial long division, which is always a little bit dangerous, we know when we take x equals 1, that's a root. So let's divide x cubed minus 1 by x minus 1, and we get x squared plus x plus 1. We can solve x squared plus x plus 1 by using the quadratic formula. And so we get 3 roots. 1, -1/2 plus I root 3 over 2, -1/2 minus I root 3 over 2. And what I can do is I can draw those 3 roots in the complex plane, and I'll label them blue, red, and green. And what I can do is I can apply Newton's method, and I can color each point in the plane based on which root I converge to. Which things do you think will converge to the red root? What do you think the condition might be? You converge to the red if you are
Negative?
okay, but we do have 2 roots that are negative, that have negative real part, the green and the red. So why did 1/3 converge to 1 and not -1? What was the relationship there? One was
It was closer.
closer. So what do you think might converge to the red root? All the starting seeds that are
Would it be with a negative x value, but a positive y value?
okay, and those ones are going to be what to the red root versus the green root? They're going to be what? They're going to be
Closer.
Closer.
closer. So maybe your guess might be, let's break the plane up to all the points that are closest to red, to green, and to blue, and you converge to whichever root is closest. Unfortunately, it's not the case. You have these beautiful fractal pictures that something fascinating is happening. And so you could be very far down in the negative x-axis, and you could be really close. You could be much closer to the red and the green, but you amazingly converge to the blue. And so the point of this is to just show that you really do have to prove things, and there can be incredibly interesting, diverse behavior lurking in the background. All right, so this goes into a lot of fractal geometry. I'm not going to go through these slides. I'm just quickly going through them right now, so you can always just hit pause, although I'll give you the links. There's also some YouTube videos that you can watch, a lot of them with really cheesy music. All right, so this finishes the quick introduction of just trying to review some of the concepts from Calc 1, essentially the algebra and some of the basis of limits and differentiability, the power of the tangent line. And then on Friday, we will answer whatever questions you have about material from Calc 1, and then we'll start the new content on Monday. With whatever time we have left on Friday, I will talk about applications and other things. All right, I will stick on for another minute or so,